So today I will discuss ANOVA. Okay, so the way we compare more than three means, and this is a topic I'm going to cover today: the theory behind ANOVA, how to use one-way ANOVA, what are the output of how to interpret the output of one-way ANOVA, then how can we use SPSS to calculate two-way ANOVA, and how to interpret the output of two-way ANOVA. Okay,
Hmm.
so again, can you tell me what is ANOVA?
Okay, it's like when there are more than two means and or more than two variables. That's when we use ANOVA. It was developed by Ronald Fisher. It is okay. The full form is analysis of variance, and it is also called F test.
And we deal with variances, not the standard deviation or standard error.
Error.
Okay,
Yeah.
in ANOVA, this is a very important point that we have to remember.
Hmm.
Okay, and okay, and this is the formula of ANOVA: true score is the variance of true score by variance of error score. Our objective is to see the effect of manipulation of IV on the dependent variable. So if there is any change in dependent variable because of IV, that is a true score.
Hmm.
And if there is any change because of some other factors which is not our, like which we don't want to know, or which we want to eliminate, that is the error variance. And we want to see whether true variance is bigger than the error variance. So this is the formula of F test. Okay.
Hmm.
Okay. Now we are discussing variance. Variance means the spread of the score around mean. So if we take square of standard deviation, that will be variance. And in variance, we don't have any sign, because as we are taking the square of standard deviation, sign will not be there. Okay. And another thing we discussed, that variance and variation are not identical. They are similar, but they are not identical. We can say that variance is the statistical method of representing variation, one of the statistical method.
Hmm.
Okay.
Hmm.
Now we'll discuss what is variance through a numerical example. So you can see here two distributions are here, two subgroup before and after a treatment, right? And these are the subject, 10 subjects. So variance means here, for the variable, for the treatment one, we have mean, summation is 80, and mean will be 8, right? So this is the mean, and these are the different score around the mean. We can see for the variable A, this is the mean, and these are the score around mean. So these are the variances. Okay. Similarly, for variable v, this is the mean 9, and other scores are there around 9, so they are the variances. Okay. So we use this symbol a square b, a square a to denote variance. Okay. So let me show in this slide. It is another distribution, same way. This is the mean. Okay. And the score around mean is the variances. Similarly, here mean is 16 and score around mean is variances. So basically, these are the two groups before, after a particular treatment, and this is the score of the same group before the particular treatment. Okay, is it clear?
Yes.
Okay. Now, so so variances, they are important. Now, if we want to see in the this example, we want to see if that particular treatment has any effect on the group. Okay, so the treatment, they cause some variation in the mean, that is called between group variation. Like in the before the treatment, for the variable A, group A, the mean was 80, and after the treatment, if we consider variable A, the mean, the sorry yeah, variable A, the mean is 100. Okay, so we can say that they have some differences, right?
Hmm.
Similarly, here also we can see that for variable B, before the treatment, the mean was 90, and after the treatment, the mean was 160. So there are some differences. Okay, so
Okay.
so treatment has some effect in the subgroup means, and this is called between group variation. Okay, so variance, is it clear what is variance?
Just give me a second. I just want to read the sentences.
Okay. I discussed basically this thing in the last class. Like we have two kind of variance. First is that we the treatment effect that we want to know, and others are the uncontrollable thing which are not in our hand and we don't want to
Hmm.
know their effect. So the treatment effect is the between group variation that we can see. Okay,
Hmm.
and other variation that not in our hand, or sometimes it may happen that that within group individual vary because of some factor. Maybe we don't want to know, we don't want to, like two groups are there, okay, and
Hmm.
within groups individuals they have some differences, like I was discussing now that
Hmm.
we have to control that that differences. Last class we were discussing on the t-test how we can do that statistically. So that is another error, within group error. Okay, so when I'm using a between group design, my objective is to see whether there is difference between two group, right? But if within a particular group there are some differences because of the individual variation, then that can be a error. Like, let me explain. Suppose I want to see difference between group A and group B.
Hmm.
Okay, now that is my objective. Now within group A, subject number 1 and subject number 2, they have some difference.
Hmm.
Okay, they have some differences because of the individual factor, because we know that it is not like that every individual they are not we are not equal, we have some differences. Okay, so we try to, whenever we design any experiment, we'll try to control the differences as like we try to control the differences, but it's not possible for us always to control the differences entirely. We need to do something, like maybe I have taken everyone now with similar IQ score, okay, but they are not same. They don't
Hmm.
have same IQ. They have
Huh.
similar IQ. So the different within subject differences are the error variance when we are using between group design. Okay, is it
Hmm.
clear?
Yes.
Okay, so uh, so an increase in the differences among the mean result in the increase in the variances of the mean. So we evaluate the how the evaluate the differences between mean relative to the error variance, and this is called ANOVA. Like I discussed in this slide, F is equal to true variance was by error variance. Okay, so
Hmm.
true variance is my objective. I want to know whether there is any difference between two group, and error variance is not my objective. So if true variance is more than error variance, significantly more than error variance, then my ANOVA result will be significant. Okay, and if the true variance is not, like there is no significant difference between true variance and error variance, then sorry, if the error variance is more than true variance, then we will say, okay, the difference is due to chance factor and there is no effect of the treatment. Is it clear?
Huh.
Is it clear now? Okay, fine. So so variance is clear now. Variance means spread of the score.
Hmm.
And when we calculate ANOVA, we consider the true variance, means the effect which we want to see, and we consider whether it is more than the error variance, relative more than the error variance. The error variance means the effect that we don't want to see, and the changes because of some uncontrollable factors. Okay.
Hmm.
Now, what is the difference between t-test and ANOVA? And another important thing is that why we can't use t-test when we have more than two means. Okay. So t-test, we know that t-test is a test which involves two means or two groups. Okay. And ANOVA or if test, it help us to evaluate three or more than three mean. That is the difference. So it is not much difficult. So I'm not discussing it elaborately. Now, why we can't use t-test when we have more than three main, right? We can use t-test, right? Means if we think, okay, maybe I have to calculate three or four t-tests, but I can do that. Why I will use ANOVA? That is a very common question, is it?
Hmm.
Means you have three groups and you want to see that whether there is difference between this group. So I can do one thing. First, I will calculate t-test between group A and group B, and then I will calculate t-test between group B and group C, and then finally I will calculate t-test between group A and group C. So I can calculate three t-tests, and then I will get the result. Okay, but if we do that, there will be a error. So to know that error, we have to know what is type 1 error and type 2 error. You have any idea about this type 1 and type 2 error?
No.
No. Okay, please remember this because this is very, very important whenever you are doing any kind of statistics. Okay, so
Huh.
type 1 error means, whenever we are doing any analysis, we make null hypothesis and alternative hypothesis, right?
Huh.
So null hypothesis means when we say the two variables are not related, and alternative hypothesis means when we say the variables are related. Okay. Now, suppose my null hypothesis is true, but I have rejected my null hypothesis. Like, suppose the null hypothesis is true that the variables are not related, but I am saying that they are related. Okay, I'm rejecting the null hypothesis. This is called type 1 error. Okay, and this error we represent by alpha. Okay,
Huh.
and type 2 error is just opposite. When we accept a wrong null hypothesis, means there is relation between two variables, but there may be something wrong in my analysis, and I accept the wrong null hypothesis that they are related, but actually they are not related. Sorry, they are not related, but when they are actually related. Okay, so
Hmm.
it is acceptance of null hypothesis, which we represent by beta. Okay, so just try to remember one, then you can automatically remember another one.
Hmm.
Type 1 error means rejecting a true null hypothesis. Now, if I use t-test instead of ANOVA when we have more than two means, first we have to calculate many t-tests. So if the number of if there are three means, then it's fine. Okay, I can calculate three separate t-tests. But suppose there are 6 or 7 groups, or 10 means, 10 groups. Okay, in that situation, if I calculate t-test, there will be many t-tests and I will get confused.
Hmm.
Right? There is a chance of that. Another thing which is very important, that is, which is called inflated error rate. Okay, so inflated error rate means, suppose I'm calculating a t-test. Okay, and I'm taking the significant of the value at 0.05 level. Okay, so it means that there is 5% chance that I will do type 1 error. Means there is a 5% chance that I will reject the null hypothesis, or I will do the type 1 error. Okay, so if there is 5% chance of doing the type 1 error, then the probability of no type 1 error is 95%. Right? Now, for suppose for three separate group of mean, I'm calculating separate t-test. Right? So I have three. I'm doing three t-tests separately, and for each t-test, I am checking the significance level.
Hmm.
Okay, so for each one, I have 0.95% chance that I will not commit type 1 error. So if we take the total, then I will do this thing, 0.95 into root to power 3, means we will do this thing into like 3 point multiply 0.95. Okay, 3.95, then we'll have this score 0.857. Is it clear?
Hmm.
Okay, now then what will be my total chance of not doing total chance of doing type 1 error? So that will be 1 minus 0.95 into 3, means 1 minus 0.857, means
Hmm.
14.3%. So if I conduct one t-test, there is a 5% chance that I will commit type 1 error, and if I compute 3 t-tests, then there is 14.3% of probability that I will make type 1 error. So you can see
Yeah.
it has increased. Okay.
Huh.
So now if I do maybe 7 or 6, 6 or 7 or 9, 10, any number of t-tests, then the
It will be
probability of doing
increasing.
it will keep increasing, right? So
Hmm.
you can see this is called family wise error or experimental wise error. Okay, so this is the formula of family wise error. You don't have, you just remember, you just have to know the concept. Otherwise, you can remember this formula only.
Hmm.
Okay, so that is the reason why we can't do t-test when we have more than three means. Okay, is it
Hmm.
clear? So the chance of type 1 error will increase. Okay, and we cannot no do that. We have to control type 1 and type 2 both error. Okay, so this is the formula of family wise error, 1 minus 0.95 n. Okay, clear?
Yes.
Clear, because
Yes.
it is a little bit twisted.
Yeah, yeah,
So
it was twisted, but then the last line you said, which, like, the probability of making increases from 5 to 14.3, so that made it clear, like the whole
yes,
concept.
yes, yes, yes.
Like, the more variables there are, the more t-tests we will need to do, which will result in more probability of errors.
Yes, yes. Just remember that more means we have more t-test we have to do, and that will increase my probability of type 1 error. So,
Hmm.
that's the reason why we conduct ANOVA, not t-test. Okay.
Hmm.
Now, assumptions of ANOVA already have discussed. As ANOVA is a parametric test, obviously normality of the distribution will
Hmm.
be there, homogeneity of the variance, and independent of the dependence score. Independent of the dependence score means the two two score, they are independent of each other. Like if we take this example, like participant 1 and participants 2, their score are independent of each other. This is very important thing when we are doing independent ANOVA. Okay.
Hmm.
Clear? And homogeneity and normality already have discussed. Homogeneity means when we assume that the variances are homogeneous. Okay. And normality means the distribution is normally distributed. So obviously whenever we are doing any kind of parametric test, we have to check this assumption. And if our data fulfills this assumption, then we will do ANOVA. Otherwise, we'll do non-parametric test that I will discuss in the last class. Is it clear till now?
Yes.
So we have discussed what is ANOVA, what we mean by variance, why we can't use t-test when there are more than two means, and the family-wise error. Okay. Now, ANOVA can be like independent ANOVA, can be one-way ANOVA, two-way ANOVA. Okay. Basically, if I discuss two-way ANOVA, then like in one-way ANOVA, we have one IV and one DV. Okay. And there are three levels of IV, sorry, three levels of IV. Yes, and in two-way ANOVA we have more than two IV. Now, if you want to do any research with more than two IV, like maybe three or four, like factorial design. Okay, so once you know how to do two-way ANOVA, you can do that. Okay, so I am not discussing that separately. Okay,
Hmm.
so today I will discuss how to calculate one-way ANOVA and two-way ANOVA. Okay,
Okay.
so one way ANOVA, as I say, there are three or more than three means, but one IV, and you have to check the significant difference between them. And one thing in one way ANOVA, we cannot see any interaction effect, because as we don't have more than one IV, we cannot see any interaction effect. Okay, and if we write the formula like we have discussed, that F is equal to between true variance by error variance. So here true variance is between group mean square, and error variance is within group mean square, because we want to know the difference between two groups. So two groups, so that is the true variance. Okay, and the differences within the group, or the variation within the group is not our concern. So if there is any difference, that is the error variance, so that will be here. And we expect that the true variance will be the between group mean square will be more than the within group mean square. Then only we can say that they have significant difference, or our IV has an effect on DP. Is it clear?
Yes.
Now, this is a numerical example. So suppose researcher is interested to know which is the effective method of classroom instruction. So there are three methods: lecture, seminar, and discussion. Okay. Now, if the participant, like there are these are three methods. Okay,
Hmm.
and researchers, they want to see whether there is any difference between the participant when they are getting these methods. Okay, and they are the DV's achievement test. Clear?
Hmm.
Now, in between group, in ANOVA, we have to divide the variance and DV in this way. First, we'll divide the variance. The total variance is divided.
What is the DF in this?
DF means degrees of freedom. I will explain you what is DF.
Okay,
Okay.
okay,
Okay.
okay.
So, we divide the variance, total variance, into between group and within group. Between group means the things on which we are interested, like the effect of method of teaching.
Huh.
If there is any difference between these three groups, okay, the group who is getting lecture method, the group is getting seminar and discussion method. If they have any different on achievement task, that is a between group difference. And within group means within this group if they have any difference. If now participant who are getting lecture method, if they have any different,
Hmm.
they differ from each other due to some reason, their achievement tests differ from each other. Maybe the day the researchers were conducting the achievement test, participant one was not well physically, maybe,
Okay.
and researcher failed to notice somehow. So maybe that is the reason why the participant
It's a
differ
more
from
like
the.
external reasons.
Yes, which are not in our hand, or which we maybe we fail to control. Okay, so if there is a difference because of that, that is not our objective. So that will be the error variance within group. Okay. Now the question is, what is DF? DF means degrees of freedom. Whenever we are calculating any test, we have to consider DF. T test also we have to consider DF. Now what is degrees of freedom? Any idea?
I know it's in the. No, I don't know. Like
Okay.
I used to think that it's on the similar lines of like the percentage of error that is acceptable.
Mm,
So
yes, you are right to some extent. Degrees of freedom, very simply, just remember. This is the way the way I used to remember when I was student, and still I use this thing. Suppose you have like this is a distribution. Okay, degrees of freedom means how many score you can vary without changing the mean. That is degrees of freedom.
can you
Okay,
repeat that? How many scores?
means degrees of freedom means how much you have, like how like you can vary, like without changing the mean, how many score you can vary, like
Okay.
only for this. If the degrees of freedom is n minus 1, it means I can only okay, I can vary 4 score, but I have to keep 1 score constant.
Okay.
Okay. Okay, so then only I can you know keep the mean the way it is. That is degrees of freedom. Is it clear?
Yes, it is.
Okay. So in t-test, just a minute. Sorry, in ANOVA, when we are doing. So, like the variance, we can divide t-test. We have to, like, we divide t-test in this two way. First is a t-test, DF in this two way. First is DF for between group k minus n. K means the number of subgroup. Okay, and another one is within group k n minus 1. Okay, this is a DF. When you are calculating in SPSS, you don't have to calculate DF separately. SPSS will do everything for us. Just you have to know, you should have the concept, that is. Okay.
Hmm.
So we can divide, that is the formula. Total mean square is equal to between group plus within group. Okay, I have written the like what we mean by these things. Okay, so I'm not explaining it again because I have already told you.
Hmm.
Okay, and then we how can we define the variable, like the numerical example discussed. If the DF is 14, okay, then total DF is 14, then out of total DF, 2 DF will come from the sorry, total DF we can divide it into 2 plus 12. Okay, 2 DF will attribute to the variation between the group, means between group variation we have 2 DF, and for the within group variation we will have 12 DF. Okay, so we don't have to calculate them separately. If we are doing manually, obviously we have to do, but if we are using SPSS, we don't have to do it. We just will DF will be there, and everything is there basically. You just have to know how to interpret it. That's it. Is it
Okay.
clear? So just remember that in one way ANOVA, we can divide DF, we can divide variance as between group and within group, and we can divide DF on accordingly for between group and for within group. Okay.
Yes.
Okay. So now the question is, when we'll use one way ANOVA. Already we have discussed that when we have three or more than three groups,
Hmm.
and the group they are independent. Okay. Now this is the steps of ANOVA. So I have to go to analyze, compare mean and one way ANOVA. So let me show you in the SPSS. We'll only consider these two column, not this one. So I'm deleting this. Is it okay? Okay. Okay. You can see we have three groups here. 0, 1, 2, 0, 1, 2. I have labeled them. Okay. So I can write it anything. Maybe it is a score of achievement test and method of teaching maybe. Okay. Then I have to add values here. 0 maybe lecture method. I'm just writing L. Okay.
Hmm.
Then 1 maybe discussion method T and 2 maybe
Seminar, I think.
seminar. Okay. Yes. Okay. Okay. Now I have to go to analyze,
Hmm.
compare mean and one way ANOVA. Okay. You can see
Yes.
analyze, compare mean, one way ANOVA. Okay. And achievement is will be dependent list. Method will be in the factor. Okay. Estimate the effect size. Activate this one. Go to option descriptive we need. Okay. Homogeneity or variance, here we have the option. Okay, now I remember we have to do the normality test also. Okay, normality test we don't have any option within ANOVA, so we have to do it separately. Homogeneity we have already here.
Hmm.
Okay, so just activate it and then means plot. Okay, and then okay, means plot today I will not explain you, so just leave it. Tomorrow I will explain you, so just leave
Hmm.
it. Continue, and you can see it is already by default written 0.95% interval, so we don't have to uh, change it. It will be there. So continue. Okay, and then we have to go for post hoc. Oh, what is post hoc? I will explain you a bit later. So
Okay.
just let me do it. Sorry. Okay. Uh, Now click OK. Okay. So this is the table we have. This is the descriptive statistics. This is the homogeneity table. We can see it is not significant. So we can say that 11 test is not significant. So we can say that this is homogeneous. Okay. And this is the ANOVA table. Okay. And this is the post hoc effect size and post hoc. Okay. Post hoc and FXS, I will explain you. Like I will explain all the tables, but before that, a few things I have to discuss. Is it clear now how you have to do? Simply go to analyze and send your data to the dependent list and
Hmm.
factors. Sorry, it is okay. I was doing with several means, so you can see many things. Many means are here.
Hmm.
Okay, but in the present example, only three means are there. So be there. Okay, and you have to send a factor group to the factor and then you have to click OK. Okay, clear. This is a step. Now we know that okay, just a minute, let me explain the table, then I will explain this slide what is poster. So here first we have the descriptive statistics. Here we'll get mean, medium, standard error, standard deviation, upper like the interval, lower bound, upper bound, everything. Okay, this is the basic information. Mainly we need mean information of mean when we want to analyze the data. Okay, you can see this is the table here. Clear? So
Yes.
and we'll get n also, then mean and standard deviation. Okay, then test of homogeneity. This already I have discussed that here we have test of homogeneity. Okay. Then next the ANOVA table. You can easily check significant between group is our true variance. So we will get significant for this one. So you can see DF is written here, so you don't have to do anything for the data. Okay. Total 29 DF, 2 for the between group and 27 for the within group, like I said in the definitions. Okay. And total 29, we can divide it like this. and if you take summation of these two, you will get this one. Okay. Now this is the, now you can see, we can see that it's not significant. So the test is not significant. Okay.
Hmm.
Now the thing is that in ANOVA we are comparing, when we are doing ANOVA we are comparing three means or more than three means. Okay. Now how I will know that what is a significant relation between two, means which two groups are significantly different. Okay. Like suppose I have five groups A, B, C, D, and E, and in ANOVA I know these groups differ from each other significantly, but I don't know, I cannot pinpoint like which two groups differ from significantly from each other. It may happen that group A and group B, they are significantly different, but group A and group C, that they don't have any significant difference. Okay.
Hmm.
That is the reason why we need to calculate post hoc test. Okay. So now the thing is that we can then we can basically post hoc test. Okay, just a minute. Post hoc test is a pair-wise comparison. We compare the pairs. Okay. Now we can do that by using t-test easily, right? Like we already said that we cannot use t-test because of that, this reason, and this kind of error can happen. But this post hoc test, they have they have we have, these tests are designed in such a way that they control this type 1 error, type 2 error. Okay. So that is the reason why we can use them without we don't have to think that if we use this test there will be type 1 or type 2 error. We can easily use them. Okay.
Huh.
So there are many post hoc tests, and before selecting any post hoc, we have to keep some points in our mind, like whether the test control type 1 error, whether the test control type 2 error. Okay. If we can use, if the assumption of ANOVA is violated, then which test we have to use. Okay. That this one you will see. So that three points you have to keep in our mind. Now, and many tests are there. Basically, in this slide, the which test, when we can use which test, everything is there. Okay, like we can use. There is an option. Like let me show you. Just a minute. If we go to the post hoc test, one way ANOVA, post hoc test, you can see many options. LST, Bonferroni, then this one SNK, Taki test. Okay, and you can see if we assume they are equally when the variance they have equal variance, we will use this post hoc test. And if we know that they are not equally they are not they don't have homogeneity of variance, like we can see easily from the 11 test, then we'll use this one, this post
Okay.
hoc test. Okay. So I have that's why it is written that you have to think we have to check whether they are homogeneous or not. Okay. And then we have like uh, like I have written here that LSD is the least significant difference. We use this, but it is very weak test. It does not control type 1 error. Okay. And it's like t-test, so we don't generally use it. Okay. Then we have two very important tests that we can use, that is Bonferroni and Taki test. Okay. But they are not, they have some bias. The best one is this one, REGWQ. Okay. Ryan Illinois Gabriel Wells Q procedure. You can see it is here. Mm.
Okay.
Just a minute. Just it's not like that you have to remember everything. You
Huh.
can
Okay.
easily refer any book, any slides and anything when you are doing the analysis. Okay, it's not possible
Okay.
to remember. Like you will, once you are, you are practicing it, you are doing
Practice.
it. Yeah, you will remember. But it's not like that you have to you can't refer anything. So you
Hmm.
can use this one. Okay. Also another test is Bonferroni. You can use this one, and if you want that, okay, I want to do more than one post hoc test, again you can do that. There is not like that. You cannot you have to choose only one. It's not like that. You can choose more than one. Okay. But it should be like your data should support this. Means your data does not have that criteria, and you are doing that test, means maybe your data is not equally it does not, that is not a homogeneous one, and you are using this one, then that will be wrong. Okay. But if it support, your data support it, then you can use any post hoc test. Okay. So just focus this slide I have written here. You can see other tests are there. Hodgberg t test, Gabriel t test. Okay. So this one here, it is very, it is, you can read this one, that when we are going to use which test, some general guidelines you can say, like if you have equal sample size and you are confident that your variances are similar, you use REG WQ, okay, or Tucky test, both. Means
Okay.
suppose your sample size is not equal, then you cannot use this one. Okay.
Okay.
Okay. Similarly, but if you okay, if sample size are slightly different, then you can use Gabriel procedure. Okay, but it is very different, then you have to use Hodgebox Z2 test. So that is up to you. You have to check your data, which one is suitable for your data. Okay,
Mm.
and if there is any doubt about the population variance, then you have to use Games Havel procedure. Okay, so like this. So these are the guidelines that you have to follow, and whenever you are presenting your data, you have to justify why you have used this post hoc, not that. That is okay.
Mm.
But if you want, you can choose more than one poster. If you think that okay, my data is they have equal sample size and I am confident that they have homogeneity in variance, so I will use both REGWQ and Taki test, then no problem, you can do that. Okay,
Mm.
you can check, and you can use also one pattern if you want. Okay, that we know that that will not create any error. You have confidence in that, then you can use that one pattern correction. It is no problem. Okay,
Okay.
is it clear? So basically the logic behind post hoc test is that you have to know the which pair differ significantly from each other. That is
Hmm.
the reason. And we cannot use t-test because that will increase type 1 error. So post hoc test
Error. Huh.
yeah, are designed in such a way that control the error. Okay.
Hmm.
There is a good book on ANOVA. I don't know whether you know it or not. That is Bruta, Experimental Psychology. I have the book with me. Experimental Design in Behavioral Research, KD Bruta. Okay, it's not on SPSS, it is on ANOVA. Okay, it's a very, very
Can
good
you
book.
put it on chat like
I
the?
can show you the book. It is the
Huh.
book. It is the book. Okay.
Okay.
It's a very good book. Okay, we used to refer this book for ANOVA. It's very,
Who's the
very good book.
author for that?
KD Bruta, BROOTA. Bruta.
Okay.
Okay, it's very good book. Language is very easy. Okay, and it's very, very good book for students to understand ANOVA. Okay,
Okay.
so clear.
Yes.
Okay, so we have discussed the post hoc analysis. So you can see this is a post hoc table. Okay, so here you can see that in this particular example, I have used a variable like this: instruction only, instruction or division presentation. So this is the mean difference I and j. Okay, and this is a significant level. You can check. So from here, we can easily say that okay, these two variables have significant difference.
Hmm.
Okay, or these two variables, they don't have a significant difference. So basically this test will give you more content for your interpretation. Okay, so more
Okay.
like you can analyze your data more deeply.
Hmm.
You can do in-depth analysis of your data. So basically an post hoc test and effect size, they will do that. Okay, is it clear?
Huh.
Next we'll discuss effect size. So here we have, like I told you how to calculate effect size in ANOVA. Like you have to just simply activate this one. Okay,
Huh.
and always use effect size, because again it will give you more clear understanding. Okay, and you will get more content to interpret your result. So always use effect size. Now in ANOVA, okay, effect size. Okay, you can see effect size here. Generally, we use eta square or partial eta square. We use eta square for one-way ANOVA. Okay, or if we want much better, then we use omega square. I've written here. This is the eta square. Okay, eta square this is a formula. You just know you don't have to remember this formula, because in SPSS, whenever you are using SPSS, you don't have to do anything manually. And the thing is that if your score is more than zero point 0.5, then it has large effect. Okay, so what you have to do, you have to multiply it with 100, your value, then you will get the percentage, right? So if it is 0.05 and you multiply it with 100, then it is 50%. So if your eta square value is more than 50%, then we'll say large effect size. Okay. So and you can get the percentage from here. Like in this case, in this data, sorry, not this one. Okay. In this data, the eta square is the score, they don't have any significant effect. So naturally, like if your data don't have significant difference, then you don't have to calculate effect size. Okay, means you can calculate to support your data, but it is generally assumed that if they don't have any significant difference, obviously the effect size will be less, right?
Hmm.
It is generally it will be. Okay, so here we can see it is very less,
Hmm.
right? If we multiply, it is very less, 0.05. Okay, so uh, it will give you the percentage. So if your effect size is 0.75, means 75% is a large effect size. But if your effect size is 5.2%, then it is a that is there is no effect size, very less, very small, right? So
Hmm.
you can easily convert it into percentage and you can interpret it, right? Or
Hmm.
it may happen the score they have significant difference, but the effect size is very small. Is not so much, not small, but it is average. Okay,
Oh.
so it can also happen. So you can interpret your result based on this thing. Okay, so any question?
No, not as of now.
Okay, here I have written that if you can use also omega square. Okay, if you don't want to use eta square, you can use omega square, but generally we use eta square. Okay, clear?
Hmm.
Okay. Now, this another way you can calculate effect size. Actually, this is the way by which we calculate partial eta square. And one thing you have to remember that eta square and partial eta square are not same. But in one-way analysis of variance, if you calculate partial eta square, your eta square score and partial eta square score will be same. Because only in one way ANOVA, partial eta square and eta square are same. Okay, so how we can do that is another method. Generally, when you are using one-way ANOVA, you will get the option there, but still you should know this one. So I have included this slide. You have to go to descriptive statistics. Just a minute. Analyze,
This.
descriptive statistics, and cross tab. Okay.
Uh,
In cross tab, you have to send. Just a minute. Okay, yeah. You have to send. Uh, achievement test in the column and method in the row, and you have to go to statistics. Here this option eta. Okay, just click
hmm.
here and continue. Here in the statistics you have an option eta. Okay, and then click OK. So this is the table you have. This is the eta square. Now you will get eta square for both thing, but you have to consider the dependent when your achievement is a dependent variable. Na method is not a dependent variable, so achievement is dependent variable. So you have to consider this one. Okay. Now this is partial eta. Now if you square this one 0.228, you will get this value. As in one way ANOVA, eta square and partial eta square they are same, so you will get this value. This one 0.052. Is it clear?
Hmm.
Okay, so you don't have to do that. Just simply activate eta square in the ANOVA option, and you will get the effect size. Okay, yeah. And
Hmm.
this is other. You can see these are the other post hoc tests that I have clicked. Okay, so the result. None of them are significant, obviously. Okay. Any question?
No, no
Okay.
question.
So okay, I have written here range is 0 to 1. So your score is, if it is more like 0 to 1, it means high effect. Okay, means you have more effect on like the effect size is large. Okay,
Hmm.
okay. So one way analysis we discuss yeah, post hoc analysis and effect size. Okay, any question?
No, no questions.
Okay, okay. Then we'll start two way analysis of variance. Okay. So suppose I want to see. effect of 2 IV on DB. Okay, then we'll use two-way analysis of variance. And when we want to see more than 2 I effect of more than 2 IV on DB, then we'll use factorial design. Okay, clear. And that can be anything, like it can be 3 IV, it can be 4, it can be 5, 6, anything. Okay, we can
Mm.
do that. But two-way analysis of, once you know how to do two-way analysis of variance, you will get idea how to do factorial design. Okay? So basically the difference between one-way and two-way is that in two-way analysis of variance, we can see the interaction effect, which is very important.
Okay.
Okay. Now, uh, again, this is a numerical example. The same example that I use in one way I have used here, but only the another IV is here, that is intelligence. Okay, so
Mm.
suppose A1 is a superior intelligence and A2 is the lower intelligence level, above average and below average. Okay, two group, two level of intelligence, above average and below average, and these are the score. Okay, now here we have two IV, so we can see the interaction effect. Is it clear?
Mm.
Here also we can divide the total variance into between group and within group, and again we can divide between group into variance for the IVA and variance for the IVB. Okay,
Mm.
and similarly we can divide the, and we have one, oh sorry, in three ways, for the variation due to IVA, variation due to IVB, and the interaction effect. Okay, and similarly we can divide the DF like this. The total DF is 29, so we can divide it like this. Okay, clear?
Mm.
Okay. And these are the steps. Okay, this is a bit different from the previous one, so let me show you. So now we'll take two IV, so two variables, we have to code them separately. Okay, so suppose it is any variable, maybe just simply I'm giving A, and this may be method. Zero, and this is another group, that is maybe gender. Now you can see, this is the, you can check it right like this.
Mm.
So we have two group. Now we have to go to analyze. Here we have to go to general linear model, then univariate. Okay. Then send your dependent variable here and your independent variable. So six factors. Okay. Now go to first go to option, click descriptive, homogeneity, and estimate of success.
Estimates of effects.
Okay. Then go to postdoc. Okay. We don't need postdoc for gender because only two levels are there. We need postdoc for method only. So just, and then you have to decide which one you have to want to use. Maybe I want to use one pyramid. Okay, then go to plots. Okay, then gender here. Why we need plot? To see the interaction effect graphically. Okay,
Mm.
right? And you have to add here this one, and then continue. Okay, and anything else we need? You can always save this thing. No, if you think that you are doing many analysis and every time you have to, adjust them, so you can easily save it here by clicking this one.
Okay.
Okay. Now, everything will happen, and then click OK. This is the table. So this is the descriptive statistics. Okay, between subject factor, and this is the another descriptive statistics. This is a 11 test of equality of variance. Okay, based on mean, we will take only this one. Based on mean, it is not significant. It means it is homogeneous. Okay,
Hmm.
and okay, this is the table. We'll consider this factors method, uh, gender and interaction. They don't have any kind of effect. Okay, they're not significant. And this is the eta square, partial eta square. Partial eta square means the effect size. Okay, this within this between subject table. So you just have to calculate, multiply it with 100, and you will get the percentage. And from there you can check the effect size. Okay, it is large, medium, or low. But as they are not significantly different, so obviously it will be less. Okay, yeah.
Hmm.
Okay, now we have post hoc test here. We have used Bonferroni, so post hoc test we have. It will be like when they don't have significant difference. So obviously, you will do the post hoc test, but it is expected that there will be no significant difference.
Okay.
Okay, and okay, this is the important thing. This is the graph. Okay, just let me go to the slide. I have written everything here so that you can remember.
Hmm.
Okay, post hoc. Okay, now this is the graph we have. So when with like the graph, if they are parallel, it means they don't have any interaction effect. Okay, but if the graph is like this one,
Hmm.
here we have interaction effect. Okay, but one thing you have to remember: interaction effect doesn't mean that this is significant. Okay, so we can use this graph to interpret. Again, we can use this to interpret our result. Maybe it is like that they have interaction effect, but the effect is not significant. So you can mention that maybe they have significant they have interaction effect with the variables, they have interaction effect, but it is not significant. So maybe because of some reason you have to explain that depends on your data or on your research. Okay, but we can check that whether we can support our data with graph. Okay, and here there is no significant difference because they are parallel. Okay, so in our data we can see this one. So we can see that the perform achievement of the participant both in male and female group, their achievement is decreasing. Like in like L group and D group, L method and D method is the same for male participant. Okay, but once we are using S method, it is less achievement, right? Similarly, we can interpret that for female. It is more in case of lecture method, and it's a bit less from lecture than discussion method, and it is very less
This.
in case of, yeah. So you can interpret many things from the graph, and which will again give us content to interpret our data. Okay, so it's not like that if your data is not, there is no significant difference and there is nothing, you cannot interpret anything. It's not like that. You can use this graph to interpret your data, right? It may happen that there is no significant difference, maybe because many times when we are doing research we have time limitation, we have other limitation, and because of that we cannot use all the data. Maybe there are no, some subjects are not there. It's very very common. Okay, you fail to take data from the subject. Maybe you have taken data for one test and you fail to take, like missing data are there. Okay, so
Hmm.
many things can happen. So it's not like that a significant difference is not there, it means my research is wrong. It's not like that. You can interpret many things from effect size, from when the data is not significant, even from there also you can interpret. And you can interpret many things from the graph itself. Okay,
Hmm.
maybe they don't have an interaction effect, but many things we can see from the graph, right? That is the reason why we need to plot that thing. Okay, is
Hmm.
it clear? Is it
Yes.
clear? Okay.
Yes.
So tomorrow, when I discuss interpreted measure, I will I'll discuss one thing that is called trend analysis for both this one and repeated measure. Okay,
Okay.
so trend analysis again help us to explain our data. Is it clear?
Hmm.
So, any question you have? Okay. Before, okay, I will analyze one more data. Okay. Uh, both. Just give me a minute. Both Excel. Anything you can take. Okay. We need one more group here. Cannot do one way ANOVA with two groups. Any score you can take randomly. Suppose there is another group. So this one we don't need. It's better if we take like n is large, but last class will do it. Okay.
Hmm.
Yes. So I'm just giving anything randomly. Maybe it is a group R. Okay. Then one is group S, and three is group not three. Two is group three. Okay. Now, if I want to calculate one way ANOVA, how I'm going to do that? Analyze.
Analyze.
Okay.
Compare.
Before that, every time I forget, we have to check the assumption of normality. Okay.
Okay.
For the variable A, only you have to check. Then uh, okay, the high chance of variable is not normally distributed, but still you have to check. Okay, obviously both of them are significant. It's not normally distributed because I have taken random data, but still, in this case, we cannot use uh, parametric. We have to use the non-parametric version of ANOVA, one-way ANOVA. Okay, but I'm just doing it for to practice, only for practice. So just tell me the step. Analyze.
Compare mean. One way ANOVA.
Okay, now
Yeah, we'll put it over to the dependent list. The A. The group is will be the factor. And wait, we had to do something in the options.
yes, obviously every time descriptive.
Descriptive homogeneity. Means plot. Do we do that?
Means plot will do if we want to check okay, the contrast effect. So, okay, I'm clicking it, and tomorrow I will explain it. Okay,
Okay.
then
Continue.
continue.
And
Uh,
post hoc.
Post hoc, they are not equally distributed. It may be high chance. I think that they are not equal. They will be like not homogeneous. Okay, which is really my assumption. So I will use this one, but I will also I don't know that whether it may happen that they are homogeneous. Okay, so for the like I will click Bonferroni, but if it is not equally equal, like if it is not homogeneous, then I will definitely consider this one. SPSS will not give me any data for this.
Okay.
Okay, so that not to be a problem because now I don't know now it is homogeneous or not. So I will click both of them. Okay, then
Okay.
continue.
Continue.
Then we'll go to another important thing.
Estimate effect size.
Yes,
Yeah.
then click OK. Okay.
So, is it like if you don't click the estimate effect size, the OK button did not appear? Was that
No,
so?
no, 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 no. If
Oh,
you don't want to see the effect size, then it will come.
okay, okay.
So we have the data here. Sorry, output here. You can see this is the trend analysis. Okay, I will explain it next tomorrow.
Okay.
Okay, so like it's like that up to certain level it is increasing, and after that it's
After that, it's
decreasing.
declining.
Okay, this is the trend we have. So this is the data. Okay, we can see the mean here, and Levin test is not significant, so it is homogeneous.
Hmm.
Okay, and between group it is less than 0.01.
0.001.
Yes, significant. And if we check the effect size, we can see it is effect size is large, 89.3%, right? Meter square. Okay, and if we consider the post hoc test, so as it is homogeneous, we'll consider this one. Okay, so
Hmm.
you can see they are significant. Okay,
Hmm.
so the difference between R and T, significant. Okay, this is significant. R and S. Okay, clear.
Yes.
Okay. So in this way we can do that. Okay, and this one I will explain you tomorrow.
Okay.
Okay. So any question?
No, no questions.
Do you want to do multivariate? Sorry, one more. And
Wait. Yeah, what were you saying? Is it too loud? The background?
yes, yes. Now it's fine. Okay,
Let's just wait for 2 minutes.
okay. Just let me enter one more variable here, group here. Okay. You can unmute.
Yeah, it's still going on. So.
Oh, no problem. We have to do it. Oh, no problem. Okay. How we are going to now? First, we have to do go to the analyze. Then this is we have two IV. So where we have to go?
Hmm.
Then enumerate. Okay. And we send. Then option. Have we click to descriptive, effect size, homogeneity. One more thing, if you want to see the power of your test, you can click this one. Okay. But
Huh.
generally we use this one. Sorry, this three. Okay. Then continue.
Huh.
Then go to plot. Then gender to here and group. You can also do like you can send a group here and gender in the horizontal axis. But I'm doing this because if then we'll get a graph which is like visually it is very nice. It will look nice. So that's
Okay.
that's why. Otherwise you can also interchange. That is not a problem.
Okay.
Okay. Okay. Then continue and then post.
Hmm.
Okay, post doc we have to. We will have postup only for
Group.
the group or gender. And this data is homogeneous, that's why it is not active. It is not
Okay.
active. Okay.
Huh.
Now everything we have, then click OK. Okay. So this is the between group design. You can see gender and gender and three groups. Okay. The homogeneity, you can see this is the homogeneity test. Partially it is square. Okay. And this is the yeah, this is the post-op test. Okay. And this one is important. You can see. Okay.
Does the gap signify something?
Yes, no, not estimable means are not plotted. Maybe there's something problem, maybe a problem in the data as it I have taken randomly, so you'll get this kind of weird graph. Okay,
Okay.
but so it's written here why it is there's a gap. So some means which are not possible to estimate, they have not plotted it.
Hmm.
Okay. So whenever you have this kind of thing, you have to go back and check whether your data is right is correct,
Hmm.
and if it is correct, then you will interpret accordingly.
Okay.
Okay, clear?
Yes.
Okay.